Everybody, hopefully you're doing well. Looks like everything is fine on my end. Maybe I'll try turning my gain up on the mic a little bit, right? So I'll be doing some problem solving today. I have a thermal exam coming up in a few days. So I'll actually be working through the solutions to some of the problems in the book Thermal Physics by Schroeder. So this is what the book looks like here. So we'll be scrolling through, and maybe I'll make a new file and get some problems worked out. So I'll see how far I get. Maybe I'll go for a good 2 hours or something like that. And we'll see where we go. So that, and we'll get to it. So starting with the first problem, we're going to chapter 1, and eventually we'll work our way to through all the different laws. So right now we'll scroll through chapter 1.2, and I may actually skip some of them. This depends on how well I know the problem. So some of them I know pretty well, and some of them I don't. Oh, 1.2 says the Rankine temperature scale, abbreviated R, uses the same size degrees as Fahrenheit, but measured up from absolute zero like Kelvin. The Rankine is to Fahrenheit as Kelvin is to Celsius. So the idea is that absolute zero in Kelvin has a direct relationship to Celsius. We just add like 273.15 or something like that to it. And absolute zero in Rankine has a direct reference to Fahrenheit. So basically what we're doing is getting a conversion between these. So we have, now you notice in the problem before that, he mentioned that the Fahrenheit temperature scale, ice melts at 32 degrees Fahrenheit and water boils at 212. The first thing I would do is I would relate this to Celsius. And we know the conversion from Celsius to Kelvin is at 273. Yeah, there it is right there. You can see my mouse. You can see my mouse right there at 273.15. So that means that 0 degrees K equals negative 270. I would have rounded to 273 Celsius. And so why don't we first get Fahrenheit to Celsius? So we can say the freezing 0 degrees, I should say Fahrenheit equals Celsius plus 32 for freezing. And Fahrenheit equals Celsius plus 112 for boiling. So we can say between these two, is 80 degrees between those in Celsius. So 80 degrees Fahrenheit equals 100 degrees Celsius. Calculator. Actually, let me see if there's a more straightforward way. I did this through a pretty long process when I did it. So let me see if the solutions actually has a more straightforward way of doing this. It just, it just have an explanation. So why don't we go through it? So 25. This is different from what I had before. We do this a different way. We can say 2 112 minus 32 equals 80, and 100 minus 0 equals 100 Fahrenheit Celsius. So when Fahrenheit goes from 32 to 212, Celsius goes from 0 to 100. So during that range, we can say that 1.8, there's a difference of 1.8 between the amount of units that Celsius and Fahrenheit goes through. So for every 1 unit that Fahrenheit goes through, is for every 1.8 units that Fahrenheit goes through, Celsius goes through 1. So we can use this relationship here. We can say Fahrenheit. So we know at 0 we have to add 32. So Fahrenheit equals Celsius times 1.8 plus 32. So if we put Celsius at 0, that'll equal 32. We put Celsius at 100, that'll be 180 plus 32. And I believe that's 212. Right, that is 212. Right, so we have that. Now we can convert Fahrenheit to Celsius. We also know that negative 273.115 degrees Celsius equals 0 Kelvin. So let's see what that is in Fahrenheit. That's negative 459.60. So that means that 0 degrees Kelvin equals negative 459.6 degrees Fahrenheit. And we know that the units are 1.8. So in other words, Fahrenheit, the Celsius and Fahrenheit, we're assuming they have the range relative to their absolutes. So Fahrenheit has the same absolute as Rankine, just as Celsius has the same as Kelvin. So this should be that we got this from the difference So that's why the solution says that Fahrenheit equals 4, I guess you should say Rankine equals 459.60 degrees plus Fahrenheit. So the conversion of 1.8 gets us from Celsius to Fahrenheit. Then I get the conversion in terms of Fahrenheit because I have the 1.8 there multiplied by the Celsius. So this gives us 0 in terms of Fahrenheit. And also to have 0 in terms of Fahrenheit, Rankine is already at the 1.8 scale because we defined it that way. So you're going to say Rankine equals 459.60 plus Fahrenheit. So it looks like when I did this problem myself, I did an extra step. So the 1.8 is already included here. I think I added another 1.8. All right. So this is what we have. The solution says saying the conversion is 9/5. Right, and that's the 1.8. So now that we have our 0, Rankine 0 equals Kelvin 0. As Kelvin goes up 1, Rankine goes up 1.8. So Rankine equals 1.8 Kelvin, where Kelvin equals Rankine divided by 1.8. Easy enough. And it looks like everything is going fine. I'm getting this error. Keyframe frequency. Change this now. Hopefully everything is going fine. Check that out later. So next problem is 1.3. Now this one I'll skip. It's just changing converting temperatures. It's easy enough. This problem here, 1.3, determine the Kelvin body temperatures for the following. Kelvin body temperature we can convert from Fahrenheit to Celsius, then Rankine, or Fahrenheit to Celsius, then Kelvin, or Fahrenheit to Rankine, then Kelvin. Boiling point, we can go from Celsius to Kelvin easily. Hold this, stay Celsius to Kelvin. Future days, we can go from Celsius to Kelvin by adding, adding by subtracting 273.15. So that's easy enough. Next problem is 1.8. So I definitely want to see what they do for this one. 1.8 is here. And does it go to the next page? I think that's part of the problem. Nope, it stops there. But let me actually make sure my formula sheet is good as well. There's a few things I wanted to add to it from my notes. Easy enough. And let me share what I have. Actually, let me make sure this moves over properly. Right, so this is the formula sheet I'm working on. I make sure that I have everything there I need. And this is Kelvin. Let me put that there. So as I go through the problems, I'll also update my formula sheet to allow us to bring one formula sheet with us. So, slightly different from what I expected. And this is from a problem earlier. For this. The problem 1.8. So it says for a solid, we define the linear thermal expansion coefficient alpha as the fractional increase in length per degree. So that is defined as change in L divided by L, all divided by change in T. So the amount of temperature increase determines how much the material expands, and is by a certain value depending on the material. For steel, alpha is 1.1 minus 10 to the negative 15, 1 over Kelvin. And that's because the units in the numerator cancel, so you're left with just 1 over Kelvin. Estimate the total variation in length of a 1 kilometer steel bridge between cold winter and night in a hot summer day. So we can just plug everything in. We want to get the amount of expansion. So that's going to be alpha equals change in L over L change in T. So change in L equals alpha L change in T equals, and it looks like they're using the annual extremes of 40 degrees Celsius or 30 degrees Celsius. So we'll say 1.1 times 10 to the negative 15, 1 over K. The length of the material is 1 kilometers, 1 kilometers. And if we use the hot plus 40 degrees Celsius and we add 273, that equals 313. And it doesn't really matter because the length scale of Kelvin to Celsius is the same, so the difference will be the same no matter if we shift it over a little bit. So we did 40 is the hot and negative 30 degrees is the cold. Let's do 40 degrees Celsius minus negative 30 degrees Celsius. So that's going to be 1.1 times 10 to the negative 15, 1 over K, and in this case 1 over C, 1 times 10 to the 3 meters, and this will be 70 C change because the difference is the same. So cancel out, and we get it's 70,000 meters or 70 kilometers. That can't be right. Let's see. There's something wrong with my units. Oh, that's what I did. Minus 1. Instead of writing a times, I did a minus sign. Right. This is better. And you this down incorrectly. E to the negative 5, not 15. Right, need to slow down a bit. Zero point 0.77 meters or 77 centimeters, given that temperature variation. He says the dial thermometer in figure 1.2. So figure 1.2 is this. They seem to be referring to this thermometer right here, this little circular thing. Uses a cold strip to make two different metals laminated together, made of two different metals laminated together, explaining how this works. But the solution says the two metals of the coil have different thermal expansion coefficients. But as the temperature increases, one expands more than the other causing the coil to coil farther in turn. And that was the answer I gave initially. C says, prove that the volume thermal expansion coefficient of a solid is equal to the sum of its linear expansion coefficients in 3 dimensions, 3 directions. So we have B equals AX plus AY plus AZ equals 3A, since they're all the same, at least for our isotropic solids. So they're saying, imagine that we have a rectangular box in 3 dimensions. Assuming that the expansion is infinitesimal, we consider it to be equivalent to adding the three shaded slabs, adding 3 shaded slabs to the volume of the solid and neglecting the corner strip omitted from the diagram. So basically what we can consider is, like if I take a side view, this is the box from the side, it would expand a little bit this way, and it would expand a little bit this way, and the same thing will happen in all 3 dimensions. And we can just go ahead and treat those 3 independently. We're neglecting a little corner strip that's right there. So volume would be Lx times Ly times Lz. The change in volume would be, so basically if this was the x side, we would have a change in Lx. That'll get longer. This will get longer. But that change will be also along the y direction and the z direction. That's only for the x expansion. And this was y, so it improve a bit. So plus the change in y, and that volume and this was z, it'll change a little bit. In that direction along the full area. So this expansion will go out along the whole 2-dimensional shape. And we know from earlier that alpha equals change in L over L divided by change in T. So alpha change in T, L equals change in L. We can substitute those in and say alpha change in T, Lx, Ly, Lz plus alpha change in T, Ly, Lx, Lz plus alpha change in T, Lz, Lx, Ly. So change in volume. And we should be able to factor this out. And now we have Lx, Ly, Lz plus Lx, Ly, Lz plus Lx, Ly, Lz. So that equals 3 alpha change in T. Volume is 3 alpha tangent T Lx Ly Lz. And since all of them are, assuming they're expanding the same in every direction, that's 3 alpha tangent T La cubed. I think that might be unnecessary. Let's see here. The book is stopping here. Referring to the definition of the volume expansion coefficient B, we see that this result has the same form. So B equals AX plus AY plus AZ, which is this. This would have been AX, but in terms of volume, and AY and AZ. Pull this out. Changing V equals 3 theta, changing T V. So B equals changing V divided by V divided by changing T 3. We know that the 3 comes from the change in V. The trick here with this one is I was never really good at proofs, that's why I gave up math as a major. So basically, writing each axis in terms of the change in that length. Equals change in T V AX plus AY plus AZ. Yes, AX plus AY plus AZ. So we can actually go change in V equals change in T V E B equals this is taking alpha and making alpha that, is beta those three alphas. Now we have the same answer the book has. Or dv over dt 1 over d alpha equals dl over dt 1 over L, right? The next one is 113. There's a mole is approximately the number of protons in a gram of protons. This is 1.13, right? So we have 1 gram of protons equals this number of them. While the mass of an electron is usually negligible in comparison. So if you know the total number of protons and neutrons in the molecule, its atomic mass, you know its approximate mass in grams of a mole of these molecules. The asterisk says the precise definition of a mole is the number of carbon-12 atoms in 12 grams of carbon-12. The atomic mass of a substance is then the mass in grams of exactly 1 mole of that substance. Masses of individual atoms and molecules are often given in atomic mass units abbreviated U, where 1 U is defined as exactly 1/12 the mass of a carbon-12 atom. So a mole is 12 grams of that. Atomic mass is about 1 mole of the substance. So 1 U is 1 mole of the substance, or 1 gram of the substance. How much mass equals 1 gram? The mass of an isolated proton is actually slightly, hold up, that's a mole of carbon-12 is 12 grams. So it's 12 protons and neutrons in carbon-12. So there is a unit table here. What page am I on? Carbon is 12. Go back in the footnote. The mass of an isolated proton is actually slightly greater than 1 U, while the mass of an isolated neutron is slightly greater still. But in this problem, as in most thermal physics calculations, it's fine to round atomic masses to the nearest integer, which amounts to counting the total number of protons and neutrons. That's a slight estimate, but it works in practical senses. Mm, Referring to the periodic table in the back of the book, find the mass of a mole of each of the following. So this seems easy enough. We just take water, which is H2O, and find the atomic mass of H, which should be about 1, and the atomic mass of oxygen, which should be about 16. And it's just times 2, so there's 2, 16. So 1 mole of water should be about 18 grams. And you do the same thing for the other. So I'll move past this one. That's easy enough. This problem is 116. All right, so we definitely have to do this one. Consider a horizontal slab of air whose thickness or height is dz. If this slab is at rest, the pressure holding it up from the bottom must balance both the pressure from above and the weight of the slab. Use this fact to find the expression for dp/dz, the variation in pressure with altitude, in terms of the density of air. Looks like we'll do the drawing here. We have a slab of air, and one of the key things uh, to consider in this problem, I give a few hints in the way they word it. So the thickness is dz, but the slab is at rest, so there's pressure holding it up from the bottom. There's pressure pushing it down from the top, and the weight of the slab. We have these three things, these three forces. We were to draw a sort of force diagram. When it comes to pressure, F equals PA. F equals pressure times area. So this is and I guess technically, this will be the area, the top of it. And we can say this is the pressure at Z plus a little bit, and this is the pressure at Z. We can put that instead of the asterisk. We'll call this Z, call this Z plus dz. So force equals negative P V plus dz A minus mg plus pz A. That's because when it comes to pressure, force is pressure times area. This is F net. All of these must balance or equal 0. So we have this as our force equation, like Newton's laws. write this a few ways. You can have it like this. You can also extract this equation out and say PZA equals mg plus PZ plus DZA, or we can say negative mg equals PZ plus DZA minus PZA. We could divide by A on both sides and say mg divided by A equals PZ plus DZ minus PZ. So these are the two forms that they put this in. A is the area of the slab, the surface area, the top area. M is the total mass of the slab. We can say that the mass of an object equals the density of the object times the volume. That's going to be the density times length, width, height. And we know the height is dz times length, width. And we know length, width is an area. So rho dza equals the mass. So we can say negative rho dz A is the mass. G over A equals P Z plus DZ minus PZ. The A here cancels. So we have negative rho dZg equals P Z plus DZ minus PZ. You can divide by DZ and get negative rho G equals P Z plus DZ minus PZ over DZ. And this is the change in P, the change in P from these 2 points. We can see the change in P, the pressure over the change in Z equals negative rho G. Right? That's an elegant bit of math. We could think of these two as change in P times A. That'll be the difference in force. But to do that so the A's cancel properly. B says use the ideal gas law to write the density of air in terms of pressure, temperature, and the average mass of the air molecules. The information needed to calculate M is given in problem 1.14. This is this. Show then that the pressure obeys the differential equation dP/dz equals negative mp/kTp, called the barometric equation. Okay. So this was A, B. We have rho equals mass over volume. PV equals N, big N, KT. Make sure I have that written properly. That's this one here. KV equals big M KT. So we should be able to just solve for V and substitute. V equals NKT over P, and 1 over V equals P over NKT. So rho equals MP over NKT. Also saying that M, the mass, the total mass, equals a number of particles times the average mass of each particle. Makes sense? So we have N, the number of particles times the average mass of each particle will give the total mass over N KT. That equals the average mass times the pressure over KT. That equals rho. And now we can substitute this and say dP over dZ equals negative average mass pressure gravity over KT. Here's the Boltzmann constant. And I believe that's what they have here. dP over dZ equals negative mg over KTP. And m is the average mass. So this is the barometric equation. Maybe I should copy this to my formula sheet. See what they did. They made a fraction line to make the superscript A. MGP, VP, it should be Z, VP DZ equals negative MG ATP. All right, that's good. We have that. Assuming that the temperature of the atmosphere is independent of height, not a great assumption, but not terrible either. Solve the barometric equation to obtain the pressure as a function of height. Pz equals P naught e to the negative mgz over kt. Also that the density obeys a similar equation, so we definitely have to look at this one. The solution says the function Pz is one whose derivative is some constant, namely mgkt. So basically we have d P of z over dz equals negative mg over kt P of z. Basically we have P prime equals negative mg over kt t. This is a differential equation. See, so rather than taking a derivative, he's actually treating it like a differential equation. Remember from office hours. So all we have to do is solve the differential equation. I initially want to go to taking the derivative or an integral. Both of them does give you the same solution, but one is easier. Treating this as a differential equation, we have the derivative of p is p times itself. So this is like saying x dot equals negative alpha x. So if x equals e to the negative alpha, this will work. That's x dot equals t equals negative alpha e negative alpha t, which is negative alpha x. So it's saying that e z equals e negative alpha z, and in this case alpha equals mg over kt. So p z equals e negative mg over kt z. All right, so you have to remember the differential equation avenue. Definitely faster than the integral way if you remember differential equations. The density Pz is just m over kt times Pz. So it has the same exponential form with a different constant out front. The constant PO times m over kt must be PO because the exponential again equals 1 at z equals 0. So you must be looking at the part that says so also that the density obeys a similar equation. here. I have to find where they got this equation from. The rho equals the average mass pressure over kT. Earlier, so rho equals average M over kT pressure. Saying density, to get this to be the same, density saying this is P of Z or rho of Z. This is P of Z. And put through an arbitrary constant up front. I remember the arbitrary constant. Z equals 0, there is still a pressure. So A must equal the pressure at Z equals 0. Because at ground level, we do still have a pressure. And E to the 0 equals 1. So at 0 at ground pressure, we'll end up having the equivalent pressure of the constant in front. Have to remember that detail. Otherwise, pressure would be 1 at ground 0, which of course is not true. But 1 times the constant will make it happen. And as E goes up, that constant will be decreased by this exponential. What they're saying is if I put in rho at 0, we have average M over KT and A and E Z equals 0, E negative mg, and that's E to the 0. So that equals P0 average mass over KT. All right. So some tricky math. And the last part says estimate the pressure in atmospheres at the following locations. Yeah, I think I missed this problem in the this part being the homework. Right? we'll take z equals 0 at sea level. So T0 equals 1 atmosphere. And T equals 280 Kelvin to be our average temperature. The air is 80% nitrogen, so the mass of molecules in kilograms is about 0.28 per mole, if the air is mostly nitrogen. Hence the quantity kT over mg is roughly always doing kT over mg. Right. Let's see what we get. T, let's do U type 1430 meters. The book problem does it a bit differently. One at 0, T, negative, let's calculate. Oh, G, okay, equals 0.28, 028 kilograms a mole, 9.8 meters per second squared. I need to put K on here. have A equals 1.381 into the negative 23 joules per Kelvin. Mm, 1.381 times 10 to the negative 23rd joules per Kelvin. Let's see what he's doing here. He's saying air is mostly nitrogen. Atomic number of 14. N2 is in the atmosphere. So N2 equals 14 times 2. That's 28. So 1 mole equals 28 grams. So 1 unit N2 equals 28 grams divided by Na equals mass of air, just about 28 grams divided by a mole. I have that here. Now gravity is 9.8 meters per second squared. It does vary a little bit with height, but we could ignore that detail for now at least. So if I multiply this by kilograms over kilograms, it's going to be 9.8 newtons per kilogram. That's what they did there. Equals 0.28 kilograms per mole times 9.8 newtons over 1.38 10 to the negative 23 joules per K. So this equals Technically, this is Avogadro's number. Maybe I should write that too. I don't remember what Avogadro's number is exactly. A equals 6.022 times 10 to the 23. Add this to the formula sheet. See what this is. Remember, I'm going to be dividing this by temperature and multiplying it by position. Dividing it by temperature, we get rid of K. Multiplying by position will see what that does momentarily. 0.28 divided by 6.022 times 10 to the 23. Zero again. 0 to 8. So that is, and considering that this kilogram will cancel this kilogram, multiply that by 9.8. 4.6 times 10 to the negative 25. A over, divide that by 38 times 10 to the negative 23. This becomes 0.033. And starting to look similar to what they had. Newton equals kilograms meters per second squared. So newtons times meters over meters equals to joules by meters. So this equals 0.033 joules by meters, K over meters. So now we're going to get no units, right? So now we can go back to our formula. PZ equals PO E negative mg over KTZ. a Boltzmann constant. And most of these we got figured out here. So that becomes POE negative 0.033 Kelvin over meters times Z over T. All right. So we make the temperature, I believe we said 280 Kelvin. And if we do Utah, and Utah is at 1430 meters. E equals 1430. We have one atmosphere. That's the atmosphere at the E0, e to negative 0.033 Kelvin over meters. And that's times 1430 meters over 280 Kelvin. Let's see what pressure at this height is. Uh, 0.84 atmospheres. And hopefully this is at least close to correct. Yep, that's perfect. All right. Well, I'll call it for tonight. Hopefully they all enjoy it. See a few showed up and see some of the difficulties with doing thermodynamics. So I may be back tomorrow to do some more problems. I'll work a few more on my own tonight. Maybe I'll get the the hardest few before Wednesday. Perhaps I'll come back and do those. So also, thanks for joining. Like, subscribe if you haven't. Barrelberry out. I'll see y'all next time.